Look at these problems. These two problems are also YDSE, but then this YDSE is performed in a different arrangement. Okay? This is not the normal arrangement. Okay? In normal arrangement, what we do is this light falls perpendicularly on the slates. Okay? Here, the light is falling at some angle. Okay? Now, can you figure out, okay, on your own, what is going to be effect? What is going to be effect on the interference here at point C? Path difference at point C, is it going to change or is it remain same? Okay. So, for example, the first question itself is this: angular position of central maximum. Okay. Do you think that we will get central maxima at point C or somewhere else? And if somewhere else, then where? Each central maxima, first question, will I get central maxima at position C? Yes or no? Okay. If no, then will it go up or it will shift down? Will it shift up or shift down? What do you think? Okay. Where do we get central maxima? Okay. We get central maxima where the path difference is 0. Okay. If I have light incident in the normal arrangement, you see this is the normal arrangement. This is the normal arrangement. Okay. So light is incident like this. This is light. Incident like this. This is my light ray. Okay. These are my wave fronts. These are my wave fronts. Okay. That means light here, and light here. They are in same phase. They are in same phase. Okay. Now at this point, this is S1, this is S2. This is the center of the screen. Now, to reach this point, both are traveling same distance. They are traveling same distance. Okay, that's why the path difference here is 0. And I get a bright fringe. We call it as 0 order bright fringe. Why? Because the path difference is 0. Now, what will happen if the light falls at some angle? Okay. Here the light falls at some angle. Okay. Now, so from here to here there is no path difference. Okay, but you see, look at the light here. This is my light. This is the light ray. It's a parallel beam of light. Okay. So these are my wave front. Okay. My wave front will be normal to this beam of light. Now, what is the meaning of wave front? These 2 points are in same phase. Okay. So these 2 points here will be in the same phase. Similarly, these 2 points here, okay, that means phase here will be equal to phase here. Okay, there is no path difference up to this point, but after this point, the phase starts to change. Now, if I compare this light S2, C, and okay, so you see up to this point here, this is 2 and this is 1 here, light ray 1. Up to this point, from here to here, they were moving in same phase. Now from this point 1 to C and then 2 to C, they are traveling different distances. What is the path difference? This is the path difference. This is the path difference. That means delta x is not 0 here. It is not 0. Delta x is not 0. Okay. This angle is given theta. Let's say that this angle is theta here. This angle is theta. Okay. This distance, the distance between the slates, this distance is equal to t. Then what will be this delta x? What will be delta x? Delta x will be equal to d cos theta. D cos theta. It will be equal to d cos 60. It will be equal to d by 2. Now what do you think? This is theta. This also is theta. That means path difference between these 2 light rays, one light ray from S2 to C, this light and this light from here. You see, these 2 points are in same phase. Phase difference starts after this point. As compared to this light is traveling this extra distance. So this will be the path difference. So at point C, this is the path difference. That means I will not get central bright fringe here. It's clear. Okay. Now, will I get a bright fringe or dark fringe? That will depend on delta x, the value of d by 2. Depending on d by 2, I can get either bright fringe or dark fringe. Depending on this path difference d by 2, I can get a dark fringe, I can get a bright fringe, or I can get any intermediate value. But it is not central bright fringe. It can be a bright fringe, but it is not central bright fringe. Because central bright fringe, delta x is 0. For central bright fringe, delta x should be 0. That means I am not going to get central maxima here. Central maxima is going to shift. Okay, we will see whether it will shift up or down. Okay, we will see. Now, let's answer this one. For what value of slit separation a bright fringe or a dark fringe is obtained at center of the screen? At center of the screen, this is the path difference. This is the path difference. Okay. Now the correct question should be this: for what minimum? For what minimum? Of course, it is not 0. It can be lambda by 2. It can be lambda. It can be 3 lambda by 2. It can be 2 lambda, but not 0. Okay. Now to get bright fringe at C, okay, what should be path difference? Delta x should be equal to what? 0. It cannot be 0. It cannot be 0. We see it is not 0. Okay, it is d by 2. Okay, this should be equal to, so 0 is not possible. Lambda by lambda, 2 lambda, 3 lambda, etc. Okay. 0 is not possible. 0 is not possible. That means this is the minimum. This is the minimum. Okay. So d by 2 is equal to lambda. Then this d minimum, it becomes 2 lambda. So if the slit separation is equal to minimum it is equal to 2 lambda, then I am going to get a maxima here at the center of screen. But it is not central maxima because the path difference is not 0. Okay. Now to get dark fringe at C, it is delta x should be lambda by 2 or 3 lambda by 2 or 5 lambda by 2, etc. Now this is the minimum. This is the minimum. Okay. So I will write d by 2 is lambda by 2. Okay. That means d minimum is equal to lambda. Minimum it should be lambda. If it is lambda, then I will get a dark fringe at C. Next 3 lambda, 5 lambda. Okay, in that sequence. Okay, so we answered this. Now let's answer the first one. Let's answer the first one. Okay, if central bright fringe is not at center, then where it is? Okay, will it be above this or below this? What do you think? This light there, this light here, 1 and C, it is traveling more distance as compared to this. At central bright fringe, path difference must be 0. That means I will have to increase this path length. Okay, so it is going to be shifted up. It is going to be shifted up. Okay, let's say that this is the position of central bright fringe. Okay, so delta x here is 0. Delta x here is 0. Okay, that means let me call this A. Let me call this A, and this point is B. Or let's say S2, that's fine. This point is P, or let's say it is C dash. Central bright fringe, it goes up because, you see, because if it shifts down, in that case, the path length of this upper light ray, it increases further. Here path difference is not 0. If I come down, the path difference keeps on increasing. Okay? I have to decrease the path difference. I have to make it 0. So it should go up. Now let's say that this position here is alpha. This angle here is alpha. Okay. What will be path difference? Okay. Delta x should be 0. Now what is delta x? Delta x is a S1. Okay. Or let's write it like this. S2C dash minus a S1 plus S1C dash is equal to 0. Okay. Now S2C dash minus S1C dash is equal to a S1. Now what is this? What is this? It is nothing but d sine alpha. This is d sine alpha. Okay, we did it when we started finding the path difference. So the path difference between this position, this light ray and this light, only this. Forget about this. The path difference between this and this only. It will be equal to d sine theta. In place of theta, I am writing alpha here. Okay. So this will be equal to AS1. What is AS1? It is d cos theta. D cos theta. Okay. So here I have d gets cancelled. The sine alpha. Sine alpha is equal to cos theta. It is cos 60 degree is equal to half. So what is alpha? Alpha will be 30 degree. 30 degree. Okay. So if this angle is 60 degree, this is going to be 30 degree. This angle here, this is going to be 30 degree. Okay. This will be the angular position of central maximum. Okay, now the next one. There is no role of this distance here. No role of this. Okay. Now, second is also a Young's double slit experiment, but now it is performed in a different manner. Okay. S1, S2, they are 2 point sources. S1, S2 are 2 point sources. At any point on the screen, this is S1, this is S2 here, S1, S2. The screen is kept like this. This is the screen. At any point, I am going to receive waves from both sources, S1 and S2 both. They will interfere. And they will also produce a fringe pattern. Now the first question, do we get a bright fringe or a dark fringe at point C? At point C here also, I will receive a wave from S2 plus a wave from this S1. I am receiving waves from both sources and then they will interfere. What will be path difference? What is path difference here? Okay. S2C, S1C minus S2C. This is the path difference. S1C minus S2C. This will be equal to this separation here. 4.5 lambda. Okay. This is 4.5 lambda. Now what kind of interference will happen? This is an odd multiple of lambda by 2. Okay. That means it is a destructive interference. I will get a dark fringe. So at C I will get a dark fringe. So this is different from our normal arrangement. Okay, so we cannot apply any formula here. It is different from normal arrangement. This is a different arrangement. It is interference, but the arrangement is changed. Okay, so we will have to think afresh. Okay, the concepts remain the same. The concepts of interference, constructive, destructive, everything remains same. Now, total number of bright fringe and dark fringe on screen. And what is shape? Okay, let's discuss this. What do you think? What is going to be total number? Okay. If the path difference here, at the center here, if the path difference here is 4.5 lambda, okay, what do you think? What will be path difference when I start moving up? Is it going to change? Is it going to increase or is it going to decrease? And what will happen if I go at a very large distance from both sources? What is going to be the path difference? What do you think? When I go at a large distance from these two sources here, you see, the distance here, okay, the path difference here will be equal to the distance between these two sources. But as I move to the large distance away from this point C here, okay, then if you look at this, these two distances are going to be almost equal. These two distances are going to be almost equal. Okay, if I am at a very large distance from here, that means at infinity here, delta x is going to be 0. But that will happen at infinity. Okay, at infinity. So here path difference is 4.5 lambda. Okay, at some point when I start moving and here is 0, that means as I go down or as I go up, path difference is going to decrease. Okay, here at some point it will become 4 lambda. Okay, then it will become 3 lambda. Okay. Then it will become 2 lambda somewhere. It is 3 lambda. Okay, somewhere it is going to become 2 lambda. Okay, then somewhere it is going to become lambda and then 0 at infinity. Okay, at infinity. Okay, here at this point here I am getting a dark fringe. Okay, here I am getting a bright fringe, then a bright fringe, a bright fringe, a bright fringe. Okay, here the last fringe that I can see is going to be a dark fringe. At infinity, delta x is 0. It is 0, but I cannot reach infinity. Okay, but I can reach here. I can reach up to this point. Okay, at infinity, delta x is 0. I cannot reach this point, but I can reach here, lambda by 2. Now, between two bright fringes, I will get a dark fringe. Between two bright fringes, a dark fringe. The same pattern will be repeated above also. Okay, here also it will be 4 lambda. Okay, then 3 lambda. Somewhere it is 2 lambda. Okay, and then lambda, and then here it is infinity, lambda by 2 here. The last will be a bright fringe, but that will be at infinity. That I cannot see, so I will not count it. Okay, so this becomes bright here, a dark, bright, dark, bright, dark, bright, and dark. Okay, this will be my fringe pattern. Now you can count number of bright fringes and dark fringes. Okay, understand this? Okay, understood? Now, if I ask you a different problem, did you see this? Okay, let's answer this. Let's answer this. What is shape of fringe pattern? What do you think? What the shape is going to be? What the shape is going to be? These two sources are perpendicular, normal to this screen here. It is already specified. Okay, so it's my screen is something like this here. This is my screen. This is the screen. Okay. Now, the two sources are somewhere here. Okay, one source is here, and then this is the other source. This is S1 and this is S2. At this point here, okay, it's like this. I have this screen. Both sources are normal. Okay, so at any point here, if I draw a circle, okay, this is the center. What is center? Okay, it is along the line joining these two S1 and S2. If I draw a radius, a circle of certain radius, okay, then at every point of this circle will be at same distance from S1 and from S2. Okay, if you consider any point, okay, that point is going to be at the same distance. So every point of this circle will be at same distance from S1 and at same distance from S2. That means delta x is going to be same. Whatever is delta x here, I will get same delta x here. Same delta x. That means the path difference will be same at every point of this circle. Phase difference will be same. Intensity will be same. If it is bright fringe, it will be bright fringe at every point. Okay. So what type of pattern I am going to get? I am going to get a circular pattern. A circular pattern. Okay. Understand this. In this case, the shape of fringe pattern is going to be circular. Now, what is the fringe pattern in a normal? What is fringe pattern in a normal YDSE setup? Okay, I have this normal YDSE setup. Okay, what will be fringe pattern? The fringe pattern here. Okay, you see, this is my center. Okay, now every point of this center, if I draw a line here, every point is going to be same at same distance. This is S1 and this is S2. Now, shape of this pattern. Okay, if I take any point P on this screen, then this S2P minus S1P should be constant. Okay, so I will find the locus of points having constant phase difference. Okay, so if I get some path difference here, let's say I get this path difference here, delta x, then I will look for all the points having same path difference. Okay, having same path difference. Okay, so it should be delta x here also, it should be delta x here, it should be delta x here. Okay, and if I join all those points, I will get a locus, and that will give us the shape of fringe pattern. Now, finding the shape of fringe pattern here is mathematically little difficult. Okay. Okay. So here we are just going to remember the standard result. Okay. The locus is, the pattern is hyperbolic. Now, why it is hyperbolic? If you have some mathematical background, or if you are having mathematics course also along with this course, then you must have understood it immediately, because this is what results into a hyperbola, a standard condition for a hyperbola. Okay. For those who are not having mathematics course along with this, you just remember it. Okay, that in a normal setup, the shape of fringe pattern is going to be hyperbolic. I am going to get the lines like this. Okay. Shape of pattern. Okay. Now, this is about Young's double slit in different arrangement. Okay, now let's say start a different topic. Let's start a new topic here. Okay. Let's start that topic with a problem. Let's start that with a problem. Okay. Let's do it like this. A light of frequency 7.5, 10, 14 hertz. Light of frequency 7.5 and 10 power 14 hertz travels in vacuum or air and then in water. Okay. So I have a light ray. Okay. So let's say that this is my light ray. Okay. So it is traveling in air or vacuum. It is air or vacuum, and then it enters into water. Okay. The question is, first question, what is wavelength? In air and in water. Very simple problem. I have a light ray, its frequency is given. It is traveling through air and then it enters into water. I have to find what is its wavelength in air and what is the wavelength in water. Direct simple problem. Okay. Second, number of wavelengths contained in 4 meter length in air or vacuum. Okay. Third. Length required in water which contains same number of wavelengths as in 4 meter air. Okay. Let's solve this problem. What is the meaning of wavelengths contained? Okay. If I consider certain length in air, this is a light wave. Okay. I can represent it like this. This is my light wave. Okay. Now from here to here, this is one wavelength. This is lambda. Okay. This is lambda. Okay. Lambda. This is one wavelength. Okay. So how many wavelengths are present in a given length? Okay. It will be simply length over wavelength. Okay. Very simple. But let's calculate. We are going to see some very interesting property. Very interesting. Okay. Now the first question. Speed is frequency times wavelength. Okay. So frequency is going to be equal to speed over wavelength. Speed, I have to find wavelength. So wavelength is going to be the speed over frequency. Okay. Now the first problem. Wavelength in air. Wavelength in air is equal to speed is equal to 3 into 10 power 8 over frequency is 7.5 into 10 power 14. Okay, does that make sense? This is going to be equal to 3, so this becomes 1 over 2.5 into 10 power minus 6 here. This will be meter. Okay, so that's it. I can write it as 10 over 25 to 0.4 into 10 power minus 6 meter Okay, so 4 into 10 power minus 7 meter. What is this? This is wavelength in air. Wavelength in air. Okay. What will be wavelength in water? Wavelength in water. Okay. It will be C over mu divided by frequency L. The speed in water is going to be different. It will be C over mu. Mu is refractive index. Okay. This is going to be equal to 3 into 10 power 8 divided by mu. Mu is 4 over 3 into, this is 7.5 into 10 power 14. Okay, let's calculate this. Okay, we are going to see something very interesting. Okay, what this is? This will be 2.5. Okay, and this becomes 10. So 15. This becomes 3 into 10 power minus 7 meter. Okay, we got this. Okay, now we got the first one. Let's look at the second. Let's look at the second. Number of wavelengths contained in 4 meter length in air. Okay, let's say that I have this wavelength. This is my light wave. My light wave. Okay, so this distance is wavelength. So if I want to find number of wavelengths contained in certain length L, okay, then this number of wavelength is going to be equal to L over lambda. Number of wavelength, L over lambda. Okay. Now, so second, N in air is equal to, it is 4 meter length here. Okay. So 4 meter divided by, this is 4 into 10 minus 7. This becomes 10 power 7. So 10 million. 10 million wavelengths in 4 meter length. Okay, so I will have 10 millions of such repetitions in 4 meter length in air. Okay, now second, N water is equal to N air. Okay, this will be length in water over lambda in water is equal to 10 power 7. Okay, so length in water is equal to lambda in water. What it is 3 into 10 power minus 7. Okay, times 10 power 7. This becomes 3 meter. Okay, what is this? This is the third part. What it is? It is length required in water which contains same number of wavelength as in 4 meter length of air. Okay, that means 3 meter length in water. 3 meter length in water contains same number of wavelength as is contained in 4 meter length of in air. Okay, that means if 3 meter length in water is equivalent to 4 meter length in air. Okay, that means if I have a light wave, okay, which travels 3 meter, okay, if it travels 3 meter in air, in water, 3 meter in water, okay, in that case it will be equivalent to traveling 4 meter in air. Okay, this length here, okay, is known as geometrical length. Geometrical length is equal to 3 meter. Okay, optical length, it is known as optical length, will be equal to 4 meter. Okay, that means, okay, what it means is, let me draw it this way. Let's say that I have this water, okay, and a light is traveling. Let's say that light goes from A to B. Light goes from A to B. Okay. So what will be geometrical length between A and B? Geometrical length between A and B will be the geometrical distance, the separation, that's it will be 3 meters. But the optical length will be equal to 4 meters. It will be 4 meters. This is the meaning of optical length. Okay. Let's do one more problem. Then it will become more clear. And actually we will derive one formula. Optical length, geometrical length. Let's understand it through one more example. Okay. Light of frequency F travels through a medium of refractive index mu. Okay. Now, first question. What length in air will contain same number of wavelengths as in length L of medium? Okay. So a light is traveling L length, L distance in a medium of refractive index mu. It will contain certain number of wavelengths. Now if I want same number of wavelengths in air, then what length is required? That will be known as the optical path. This is the geometrical path and that will be optical path. Okay. Now let's do one more. Okay. What is time taken? Okay, T naught to travel distance L in medium. Okay, and then third part. Okay. What is distance traveled in air in same time t. Very interesting. Okay, in t naught, in 1 second, this light, no, not in 1 second. Okay, let's say 1 meter. To travel 1 meter, the light is going to take some time. To travel 1 meter in medium, light is going to take some time. In the same time, what distance light will travel in air? That will be its optical path. Okay, let's see what answer we are going to get. Okay, wavelength is speed over frequency. Okay, number of wavelength is length over lambda. This is number of wavelength. Now first case, what length in air will contain same number of wavelength as in length L of medium? Okay, so n in air is equal to n in medium. Okay, this will be L in air over lambda in air. Okay, this I can write as L over lambda. It becomes V, LF over V. LF over V. Okay, will be equal to L medium over lambda medium. Okay, this will be equal to L F over V mid air is equal to L medium F. Frequency remains constant. Okay, over V in medium, and this will be equal to LF over V. V is equal to C over mu. Okay, so this becomes mu LF over C. Okay, see how we are solving this. So LF over mu of air, this is air. Okay, so mu of air and L in air over F is equal over C. C is a constant, okay, is equal to mu of medium and L of medium and F over C. F and C will get cancelled. Now this is 1 and length in air is mu times L. This is known as optical path. Okay, so a geometrical path of L in a medium will be equivalent to an optical path of mu L. Okay, geometrical path of L in a medium of refractive index mu will be equivalent to geometrical path of mu L in air or vacuum. This mu L is known as the optical path. Optical path. Okay. Okay. So we have this formula. Okay. Optical path is mu times geometrical path. Optical path is mu times geometrical path. Now let's look at the second part. Second, what is time taken? T naught. I am calling it T naught to travel distance L in medium. Okay, time is equal to, okay, the second part, T naught is equal to L over V. It is equal to L over C over mu. Okay, so mu L over C. Okay, all right. Now, so this much time is taken. In the same time, how much distance the light will travel in air or vacuum? Okay, so third, L in air is equal to C times T naught. It is mu L C times mu L over C. It becomes mu L. Okay, this is known as optical path. Okay, so we understand optical path in two different ways, and both are equivalent. Okay, now why we are doing this? What is the purpose behind doing all this? The purpose is very important, very significant. What is the purpose? What is the significance of optical path? Okay, what is significance of optical path? Okay. Answer is, it is used to calculate path difference, phase difference. Okay. In this relation, delta phi is equal to 2 pi over lambda into delta x. Okay. In this relation, delta x is equal to optical path. Delta x is not equal to geometrical path. The first time we are doing this. Till now we have been doing this blindly, without ever referring to this concept. Then all of that was incorrect? No. All of the experiments, if you try to recall carefully, all of the experiments were performed in air. Okay, so in air, optical path is equal to geometrical path. Okay, in air or vacuum, okay, optical path is equal to geometrical path. So it does not make any difference. You understand this? Okay. Now let's do a few problems. Just remember this relation: optical path mu times geometrical path. Two light rays initially initially in phase pass through two different paths of length of same length L as shown. Okay, find optical path difference. Optical path difference. Optical path difference. Not optical path, but optical path difference. Find optical path difference between them. Okay, let's see first case here. So I have this L length here. Okay, L length. Let's say that this is my first line. This is the first path. This distance is L. This distance is L. Okay, so I have two different paths. This is the first light, and this is the second light. Okay. Both are in air. This is in air. This also is in air. I have two light rays. Both are in phase. That means up to this point both are in phase. Then they are traveling L distance along two different paths. Okay, I have to find what will be the optical path difference between them. Initially there is no difference. Both are in phase. Okay. Second, let's say that this also is distance L. Now, one light is traveling through a medium. Let's say that it is traveling through a medium of refractive index mu. Okay, and the other path, the other light is traveling in air. Both are traveling L distance. One is traveling through air, and the other one is traveling through this medium of refractive index mu. This is refractive index mu. Initially both are in same phase. What will be phase difference here? Okay. Now let's look at one other problem here. Okay, this distance here is equal to, let's say it is equal to L. Of course it is equal to L. Okay, then this is air. This is air, and this is here some medium. Okay. Now the refractive index of this medium is mu, and its thickness is T. This thickness here, this length is equal to T. What will be optical path difference? Okay. Or let's say one more problem here. It's like this. Okay. This is one medium here. It is mu1, one medium mu1, and then there is one other medium here. This is mu2. The light is traveling same distance. The distance remains the same. This is equal to L in both mediums. In both mediums, the geometrical length is same. Geometrical length is same. Optical length, the optical path will be different. Okay. So we have to find the difference between their optical path. Okay. What do you think? Can you answer it? And then we will do one more problem. Let's do it quickly. Optical path difference is equal to optical path of light 1 minus optical path of light 2. We are concerned only with the magnitude. Okay, a path difference of lambda is same as path difference of minus lambda. Okay? There is not much difference as far as the resultant final result is concerned. There will be no difference. Okay, same type of interference. It is going to be constructive interference. Okay. Now, so here it is, and optical path is equal to mu times of geometrical path. Geometrical path is same. It is traveling L length in first case. Okay. In the first case, OPD is equal to mod of, okay, length mu. So L minus L is equal to 0. In air, optical path is equal to geometrical path. Geometrical path is L, optical path will also be L in both cases. Okay, it is 0. Second case, OPD is optical path difference. Now this is traveling the entire distance. The geometrical path in this medium will be equal to L. Whatever is the separation between these two ends. Optical path will be mu times of this. Okay, it becomes mu times of L minus L. Okay, so mu minus 1 times L. Mu minus 1 times L. Okay, understood? Now third case. OPD is equal to OP1. What is this? This is air, it is equal to L minus. What is this? It is traveling some distance in air and some distance in this medium. Okay, this second light, this is the second light ray. It is traveling some distance in air, this distance, and some in the medium. Okay. What is distance traveled in the medium? Okay, it is mu times t, okay, plus what is distance traveled in air? The remaining L minus t. This is the total optical path of second light. It is traveling some distance in the medium. So optical path corresponding to this will be mu times t. Remaining distance, it is traveling in air. In air, optical path is same as geometrical path. Okay, so I am adding this like this. Okay, mod of L minus mu t. Okay, minus L plus t. Okay, so here I am going to get it is going to be t minus mu t mod of this. So it is going to be mu minus 1 times t. That's it, mu minus 1 times t. We are concerned with the magnitude. Okay, mu is always more than 1. That's why I am writing it in this way, mu minus 1 t. The third case. Okay, let's look at the fourth case. Okay, let's see. You also try to get the same answer. Let's do it. Fourth case. OPD is equal to mu 1 times L, mu 2 times L. That's it. So mu 1 minus mu 2 times L. Okay, mod of this. I have to report the positive value. Generally we report positive value. Does not make any difference. Path difference of plus lambda, same as path difference of minus lambda. It makes no difference. Both cases I am going to get constructive interference, bright fringe, same intensity. Okay. Now let's do one more. Okay. One more. And the result of that we are going to remember. Okay. The fifth case. The fifth case is like this. Let's say that I have this light here. This is S1, this is S2, this is point C. Okay, so I have two light rays. Okay. S1C is equal to S2C is equal to L. Let's say. What will be path difference? So these two light rays, they are arriving at the same point C. They are going to interfere. There will be interference. What will be path difference here? Path difference here will be 0. Bright fringe. Constructive interference. Now what will happen? Okay. Obviously, I think, okay, I don't need to explain. Path difference is 0, bright fringe. What will happen if I put here a very thin medium? Okay, a very thin medium here of refractive index mu and thickness is t. Okay. T is small. Okay. A thin plate, let's say. A thin plate of thickness t. Now what will be optical path difference between these two light rays? Both distances S1C and S2C is equal to L. What do you think? What will be path difference? And this is the result that we are going to remember. We have to memorize this. Remember this result. Okay. So in the fifth case, what is optical path difference? Okay. What will be optical path along this line? This light ray is traveling some distance through this medium. What distance? If it is thin, you see, if it is a thin plate, okay, then this distance will be approximately equal to this distance. If both are, if it is very thin, in that case, these two are going to be equal to T. It will be thickness of this plate. Okay, so this light ray, it is traveling some distance in the medium and the remaining in air. This light is traveling all the distance in air. Okay, what will be optical path difference? It will be equal to optical path of first light mu times T plus L minus T. This much distance in medium and remaining distance in air. This is the optical path of first light minus optical path of second light. It is equal to S2 and C. It is equal to L. Okay. So now I have this. So mu T plus L minus T minus L. What do I get? Mu minus 1 times T. Okay. Remember this. It is a very important result. Okay, let's look at some application of this. We are going to look at some very important application of this result. The optical path difference is going to be mu minus 1 and mu minus 1 T. Okay, let's say it's like this. Okay, we are going to discuss a very important case. Try to understand it carefully. In the next lecture, we are going to do problems based on that concept. Okay, and the concept is very important. In almost all of the exams, they ask questions based on that. Okay, let's see. It's like this. It's like this. I have this normal setup, YDSE setup. This is the center of the screen. This is S1, this is S2. S1 and S2. Okay. Now, at this point, light from both sources arrive. What is delta x? Is equal to 0. Delta x is 0. I get central bright fringe. I get central bright fringe at the center of the screen. Okay. Delta x is 0 because these both path lengths, the optical path, geometrical path as well as optical path, both are same. Because both lights are in air. Now consider this. What will happen if I cover okay, this is S1, this is S2, this is center of the screen. Okay, now both are same, no difference. No. The question is like this. What will happen if I put a transparent sheet here, a thin transparent sheet? Let's say that its refractive index is mu and its thickness is T. Do you think the path difference here will be 0? Geometrical paths are same, like this here. Here also geometrical path S1C and S2C are same, but optical path is not same. So there will be optical path difference. Because of that, there will be phase difference. Okay, now here the optical path difference delta x, geometrical path difference is 0, but but optical path difference is not 0. Okay, so this delta x is not 0. So will not get central bright fringe. Note it down. At the center of the screen, if I put a transparent sheet here, any transparent material, it can be glass, it can be plastic, any transparent material, if I paste it in front of one sheet, one slit, one opening here, then I will not get central bright fringe here, because the path difference will not be 0. Path difference will not be 0. Okay. Now, if I do not get central bright fringe here, then where will I get it? Where will I get it? Okay, I will get it somewhere else, wherever the optical path difference becomes 0. Now, does it become 0 above this point or below this point? Okay, what is the effect? Okay, what is the effect? Okay, central bright fringe, okay, does not form at center. Okay, then where does it go? Is it shifted up or down? Is it shifted up or down? And by what distance? By what distance? Okay, what is the answer to this? Okay, so if the central bright fringe is not here, then it will be either above this or below this. Now, why it is not here? Because path difference is not 0 here. Why path difference is not 0? It is because optical path of this ray is more than this. Optical path of this is more than this. Now, I want to locate central bright fringe. Okay, in that case, both path must be same. The optical path of both must be same. This is already more than this, so I need to increase this. That means that can happen only at a point above center. It can happen only here. Only here it can happen. Okay, at this point, delta x is 0. Let's say that this distance is y. Okay, this is the new position of central bright fringe. Okay, so it shifts up. It shifts up, and along with it, whole fringe pattern shifts up. Okay, so if I do not have this sheet here, this transparent medium here, then I get central bright fringe here. Okay, and then the whole fringe pattern will be symmetrical to this. Okay, now the moment I keep it, then the whole thing is going to shift up. Okay, so if I cover this upper slit, the whole thing is going to shift up. And what will happen if I cover this lower slit? Then the whole thing will be shifted down. Okay, so central maxima, the position of central maxima will shift up, and along with that, the whole pattern will shift up. Okay, now what will be shift? By what distance? Okay, so it will be shifted. The central bright fringe will be shifted to a position where delta x is 0. Okay, let's see this. Okay, so delta x is 0. Okay, so optical path along SC1. Okay, that means optical path along SC1, this path is equal to S2C. Is optical path along S2C. Okay, is that right? Optical path along S1C is optical path along S2C. Okay. Along S1C, it is equal to mu times T plus S1C minus T. Now think about it. Along this path S1C, the light is traveling some distance in this medium, remaining in air. Okay, so S1, okay, it is S1C dash, S1C dash here. Okay, now is equal to, along S2C, this whole thing is traveled in air. It is simply equal to S2C dash. That's it, okay. Now, mu T minus T is S2C dash minus S1C dash. Now, this is a standard relation. I know it already, okay. It is equal to D into Y over T. Okay, that's it, okay. So, this Y is equal to mu minus 1 into T into D over D. That's it, okay. Or you can change it in different form, okay, using this relation. So do you understand this? Okay, I'm going to clean all this. You have to note it down. You have to remember it. If you paste something in front of upper slit, the whole thing is going to shift up. If you paste something on the lower slit, the whole thing is going to shift down. Okay. Now this thing I can rearrange in different form. Okay. I know that omega is lambda capital D over small d. Okay, so this capital D over small d is equal to omega over lambda. Okay, I can write it as mu minus 1 into T into omega over lambda. Okay, in different forms it can be arranged. What is this? This is shift in position of central bright fringe. Okay, Y is equal to, let me write it here, mu minus 1 T into D over small d here. Okay. Now see what will happen. Okay. If I do not have it here, if I do not have this sheet, central maxima is going to be here at the center. The moment I keep it, everything is going to move up. Okay. So if I observe any point on the screen, I will see the fringes shifting. I will see that some number of fringes will shift. Okay. So what is the number of fringes? Okay. What is the number of fringes that shift? Okay. Now this whole thing, so central bright fringe was here. Now it goes to this position. So whatever was the number of whatever were the fringes contained here, all of them will shift up through any given point. Understand this. If I do not have this sheet here, central bright fringe is here. The moment I paste this sheet, everything is going to shift up. So whatever fringes were present in this region, okay, in this region, because central bright fringe is shifting from here to here. So whole pattern is shifting up. Okay. So whatever fringes were present here, that many number of fringes are going to shift. Okay, shift up. Okay. So what is the number? This number n is equal to y over omega. Y over omega. Now this is going to be equal to mu minus 1 T capital D over D divided by lambda D over D. Okay. So this number of fringes that shift is equal to mu minus 1 times T over lambda. This is something that you have to remember. Remember this. Okay. This is easier to remember. Now once you remember this, okay, you can easily find y. Okay, y will be simply n times omega. Okay, these many number, this can be 4, 5, 6, whatever it is. These many number of fringes are going to shift. When one fringe shift, that means the pattern shifts by one fringe width, omega. So if n numbers shift, it is going to shift by n times, n omega. Okay, now there is one other thing. Okay, there is one other thing that you can correlate it with. Okay, it's important to correlate things. It's important to correlate things. It's like this. It's like this here. Okay, let me do it again. I have this arrangement. Okay. Delta x here is 0. It is 0. But if I keep it here, if I do not have it, path difference is 0, I get central bright fringe. Okay, makes sense? If I keep it here, mu and t, then delta x is not 0. It is not 0. Then what it is equal to? If it is not 0, then what it is equal to? It is equal to delta x here is equal to mu minus 1 times t. We just did one problem, okay, in the previous section. This is the path difference. Now this clearly is not 0. It clearly is not 0. Then it can have any value. If it is not 0, then it can have any value. Okay. It can be lambda, it can be 2 lambda, it can be half lambda, it can be 1/3 lambda, it can have any value. At this point, I am not going to get central bright fringe. Okay. But can it be a bright fringe? It can be a bright fringe depending on this path difference. It can be a bright fringe, it can be a dark fringe, but not central bright fringe. Okay. Let's say that this delta x, let's say that mu minus 1 times t is equal to lambda. Okay. Then what will happen? The bright fringe, the central bright fringe, at this position I am not getting central bright fringe, but I am getting a bright fringe. Okay. Then I will have a bright fringe here and central bright fringe will shift here. This will become central bright fringe. The new position. Earlier the central bright fringe was at this position. Now it will shift up. How many fringe will shift? One fringe will shift. Okay. So through if you observe this point, through this point, one fringe will shift. Okay. The central bright fringe that was here, it will shift and it will go up. So if you observe this point, one fringe will shift. Okay. That means path difference of lambda equivalent to one shift of one fringe. Shift of one fringe. Okay. The path difference of 1 will be equivalent to 1 over lambda. Okay. Shift of 1 over lambda fringe. Okay, then path difference of mu minus 1 times t will be equivalent of mu minus 1 times t over lambda fringe change. That's how also you can relate and you can keep it in your memory. Okay. The more connections you make, okay, the more are the chances to retain that thing, and the more are the chances that you will be able to develop an intuition, a deeper understanding into the concept. Okay. So remember all these things. Next class we are directly going to do some problems, okay, based on this.